right, so good afternoon, everyone. Welcome to our Ezra's Roundtable Systems Engineering Seminar program. This is our very first seminar for the semester. I hope everybody stays warm in the winter storm. It's my great pleasure to introduce our distinguished speaker, the very first one of our semester. It's Dr. Corinne Scown from Berkeley Lab. So as you may see, her biographic from the announcement. So Corinne is the vice president and founder of the Life Cycle Economics and Agronomy Division at the Joint Bioenergy Institute. She's also a deputy director for research of this energy analysis and environmental impacts division at Lawrence Berkeley National Lab. She also holds the title as the head of sustainability at the Energy and Bioscience Institute. So Dr. Scown's expertise includes life cycle assessment, techno-economic analysis, biofuels and bioproducts, and co-management of energy and water or energy-water nexus. She has led many projects funded by U.S. Department of Energy, California Energy Commission, California Air Resource Board, Energy Bioscience Institute, and she also frequently collaborates with many companies in the private sector, ranging from small startups to large multinational corporations, related to bioenergy and bioproducts. So she earned a bachelor's degree in civil engineering with a double major in engineering and public policy at Carnegie Mellon University. I don't know if I ever overlap with her at CMU, so I got my PhD there. So wonderful time. And I think she received a PhD and MS degree in civil environmental engineering at UC Berkeley. And currently, she's also teaching courses in UC Berkeley. Right, and also I want to add very briefly that she was recently recognized as one of the very distinguished award by American Chemical Society as the ACA Sustainable Chemistry and Engineering Lectureship Award. So that was a very prestigious honor as well. So please join me to welcome Dr. Corinne Scown to our seminar program today. And what she's going to talk about is in the area called overcoming the engineering and environmental challenges of achieving a more circular economy. Corinne, it's yours.
All right. Thank you. Thank you for such a nice introduction. Okay, let me. So I won't spend much time on this slide. Besides just to say that I've been doing a lot of work in bioenergy basically since I started my graduate work. By the way, I left Carnegie Mellon in spring of 2007. So I don't know if we overlapped or not, but
yeah, I guess so. It started in 2005, so we probably see each other somewhere. Maybe the food truck, right? One of the food trucks.
Yes. And back in around 2015, I started working not so much on kind of dedicated crops and converting those to biofuels, but more on the idea of converting organic waste to energy. And so I worked on organic waste for a while. And then more recently, just in the last few years, I've started working specifically on plastics. So some of the first projects were around kind of bio-based plastics, development of novel polymers, et cetera. But we also kind of got into just the infrastructure requirements for recycling plastics and novel processes for recycling conventional plastics that we use today. And so those are the two kind of big pieces I'm going to touch on. Is I'll talk about an organic waste project and then a project that's focused on plastic waste, all kind of under this umbrella of the so-called circular economy. So one of the challenges that I see about developing solutions for achieving a more kind of circular economy is that it's a nice thing to say, but it's a really multifaceted problem. So this is not like climate change mitigation, where we have like a very straightforward goal, right? Like we have emissions, we have, the sort of GWPs for all of these different greenhouse gases, and, we can measure progress in like a single metric, right? CO2 equivalents. I mean, there's certainly some nuances there, and you can do things like change albedo that aren't directly related to emissions, but like on the whole, I think that's a way easier problem to tackle in terms of like measuring your progress and weighing different options. The challenge with achieving a sort of quote unquote circular economy is like there's a lot of different problems that we're trying to solve all at once, and at any given time, it's not entirely clear sort of which ones we should be prioritizing. So kind of a multi-objective optimization problem, right? For you systems folks, this is what we're tackling here. So what are the problems we're trying to solve? Here are a few as I see them, right? Resource depletion, right? We want to keep more oil in the ground. We would like to recover nutrients that are useful from, organic materials, any other components that might be useful. I mean, in the case of like critical materials, maybe we want to recover, metals that are scarce. We want to create supply chains where, we're not relying so heavily on just a few countries that may or may not be politically stable for supplies of these really important elements that we need to create things like batteries, et cetera. We also want to avoid accumulation of waste in landfills. The degree to which accumulation of waste in landfills is a huge problem on its own is like, that in itself is a really interesting question, because certainly in the US, we have lots of land, right? And redevelopment of landfills, though, is really expensive. And so if you're going to do it near a populated area and you want to be able to do something with that land later, like we are sort of, you're going to have costs down the line if you want to use that land. Otherwise, it's just wasted. Accumulation of waste in the environment, right? Huge deal. You talked about this garbage patch in the ocean, et cetera. Climate change. Certainly some of these things that we produce, kind of virgin materials for, are, they're emissions intensive. Ethylene is a really, really greenhouse gas intensive chemical to make. And we need that for, polyethylene terephthalate, high density polyethylene, low density polyethylene, right? And so finding ways that we can recycle those materials in an energy efficient way does, to some degree, address issues of climate change, and then human health impacts associated with the way that we manage our waste. And I'll get more into the details of that, an example of where it really matters. So this is California data, but this is a kind of representative breakdown for the US. So you can look at this and kind of gauge, what sort of waste are we generating at the municipal level. So one of the things that I think people who've been following the news may be kind of surprised about is like, plastics are not the majority of the waste that we generate and send to landfills, right? We generate way more organic waste, paper, which I would sort of lump under organic waste, right? Paper, cardboard, et cetera, than we do plastics. And so if our goal is to mitigate the accumulation of waste in landfills, you should probably start with organics, because those things, they will degrade quickly at first. But once, a cell is capped off, it's fully anaerobic, it's staying there, like, it slows way, way, way down. And so there's still a fair bit of organics that just stay in our landfills for many years. Plastic waste, does stick around longer, right? That breaks down way more slowly than organic material. But it's also, I view it as a sort of problematic contaminant that prevents us from being able to recover and easily recycle other things that we need to recycle. So plastics has this kind of like secondary effect on our ability to divert things from landfills. So in the first project I'm going to talk about, we're tackling, I think, primarily these three issues, right? Accumulation of waste in landfills. I'm going to talk about organic waste, and that is the majority of what we send to landfills. Climate change, talk about why landfills impact climate change, and then human health impacts. So for those who are not acquainted with the way landfills work and why we care about them from a climate change perspective, this is like a very short primer on why landfills emit methane, right? Methane emissions happen because of the anaerobic decomposition of organic material. And so you might say, well, especially for a case in California, all of their landfills are very responsibly managed and they have gas capture systems, and you recover that gas, it's about 50% methane, as a fuel, or at least flare it. But that's not the whole story. With landfills, you have what's called a cell, and you load organic material into that cell. And while you're loading it in, the gas capture system is not recovering landfill gas. It only starts recovering that gas when it's capped off. The cell is full, you cap it off, your capture system is in place. And so for anybody who has like left, produce out at ambient conditions, that food waste breaks down really fast. And so that stuff will begin to break down anaerobically before the cell is capped off. And in some cases, more than half of the total methane that it's going to generate over its lifetime in the landfill will actually escape the landfill before the cell is capped off, right? It just breaks down really fast. It's nitrogen rich. There's plenty of like carbohydrates and stuff that the microbes can eat really easily and really quickly. And so that's just what happens. So landfills are a significant source of methane. All right, the other piece here that's important is manure management. At confined animal feeding operations, CAFOs, we take manure and put it in these lagoons. So you are creating effectively an artificial wetland, right? Like perfect conditions for anaerobic decomposition of that material, and that methane just gets emitted to the atmosphere. There are efforts to change this, and in some cases they're moving towards sort of covered lagoons and recovering some of that biogas, but there's still a lot of uncovered lagoons in the US. So this is just to show you, like, I'm not making this up. There's a lot of methane emissions that occur from manure management, wastewater treatment as well, and landfills. Some of the super emitters in California are landfills, and that was demonstrated in a 2019 paper published in Nature, where they were taking measurements aerially. Okay, so in this project that I'm going to talk about first, we partnered with it's called the Zero Waste Energy Development Company, and they built what was at the time the world's largest dry anaerobic digestion facility. And when I say dry, I don't mean literally dry. That waste is still really wet. What I mean is that the organic material can be in a pile. It's not pumpable. It's like you shove it into a big, like, sort of shipping container sized unit, close the door, you sort of spray and recirculate leachate, but it's not something that you would put in a big tank with water the way you would at a wastewater treatment site. That would be a wet anaerobic digestion system. So you can think of it as like pile is dry, pumpable waste in a big tank, like wastewater treatment, that would be a wet system. So they take in all kinds of organic waste from the city of San Jose and surrounding cities, including Palo Alto and a few other places. They have the capacity to process 90,000 tons of organic waste per year. Most of that is very contaminated, and I will show you some pictures of what that looks like in just a second. They take that biogas and they burn it to generate heat and electricity. They need heat to run the digesters. They're what's called thermophilic digesters. So they operate at high enough temperatures that you do need a supplemental heat source. They don't, like, the microbes don't generate enough heat on their own to sort of keep that particular community happy. And when they burn the biogas, they also export 1.6 megawatts of electricity, or at least that's their maximum capacity. Often it was a little bit below that, but not too far below. This is a simplified process flow diagram of what happens, right? They're taking in green waste, municipal organics, which just by eyeballing it, I can tell you it's mostly food waste. And that's the data suggests that that's true for municipal organics. And then a small amount of manure. Manure is not the majority of what they take in. All right, it's highly contaminated. I have seen things like couches show up at this place, right? So they're separating out recyclables, bottles, aluminum cans, that stuff, sending it to a recycling facility. They also have to separate out a lot of just trash that goes to a landfill. The organics are going into the anaerobic digester, still very contaminated. You'll see lots of plastic still in there. This is a batch process, okay? So you close the door, you start it up. The way these facilities start up, it's almost like sort of passing a sourdough starter along among your friends. Like, they get an inoculant from like another thermophilic digester. I can't remember what facility they got theirs from, but like that's how you sort of start up the microbial community. And then it stays in there for, I believe it's 21 days. You open it up, half of the mass is still there at the end of that process, right? And then that half of sort of remaining organic material is basically sort of processed to a degree on site and then shipped off to be composted, and that is eventually sold as compost. So our research questions in this project were, is this a good way to manage our organic waste? Does this provide net greenhouse gas benefits? How big are they? What kind of impact does it have on human health? I mean, we just knew from measurements that the team was taking that, there were plenty of pollutants that have an impact on, like, particulate matter concentrations in sort of surrounding areas. So we wanted to understand what those impacts were. There hadn't really been a study like this where you were able to sort of track everything end to end from like the moment the waste is dropped off, actually before, because we had all their delivery logs, we knew where it was being shipped from, all the way to the end where you have finished compost and you've generated energy. and say, like, with empirical data, like, is this a good strategy? Is it not? How does it stack up to our alternatives that could have been pursued? Will dry AD still offer those net benefits when we take into account real world practices? One of the challenges with LCA is that people use sort of idealized data, best practices from industry, rather than reflecting what is actually happening at these facilities. Like, you know, waste management is just a messy business. You know, nothing goes sort of perfectly according to plan. And so you really want that real world data, especially for a sector like that, because ideally this data is of limited usefulness. And then if we take the climate impacts, the health impacts, or net positive and negative, right, and we monetize them, we have ways to turn this into social cost. Do the high tipping fees that this facility was guaranteed by the city make sense? Are there better ways we could have spent that money to achieve similar or better outcome, right? A societal outcome. So these are the detailed operations, and I don't need you to, you know, like spend many minutes trying to interpret this chart. What I want you to take away from this is two things. The first is that at a facility like this, your waste is always decomposing, right? It's decomposing from the moment it gets in the door, and it can sit there for as much as 48 hours by law before they do have to process it. And then in a batch process, you have these sort of startup and shutdown times. And so, you know, there's quite a bit of gas that has a methane concentration that's too low to be usable. And so most of the complexity at this facility is all around dealing with these different streams that have methane concentrations that are too low, right? So if you have a stream that has less than 2% methane, you can send it through what's kind of called a biofilter. So they have these giant, like, cylindrical units that are wood chips covered in biofilms, and the microbes in those biofilms sort of eat the organic material that's in the gases as it sort of percolates through, and you're just trying not to emit methane to the atmosphere, or like minimal methane to the atmosphere, right? If you have 2 to 20%, you know, you want to flare it, but also it may not have enough methane in it to ignite in the flare. So then you have to supplement it with rich gas, right? So you're taking usable gas and then you're supplementing this other gas just so you can get the fuel content high enough for it to even burn. So there's a lot of wasted methane in this process. And we also didn't know how all these emissions controls were working. So we took some measurements to really understand, like, how much methane is this place, you know, leaking, which are fugitive emissions. And the other thing I pointed out before is that half of the mass of the material is still left afterwards. And that's a significant cost driver. And it's also a driver of environmental impacts, as we'll talk about. These are just pictures from this facility. We spent a lot of time there. I got very accustomed to the odor. It's, yeah, you know, I've never had such a intimate relationship with a waste management facility before, but it was useful in the modeling to really sort of see the day-to-day operations and have access to all of their sort of software that they use to control the facility. I mentioned that the waste was very contaminated, and so now you can see for your own eyes what that looks like, right? This is pre-digestion waste, and this is post-digestion. So you can see, just like, you know, if you left a banana on the counter for a long time, it turns sort of dark brown, black color. But there's a lot of plastic bags in there, a lot. Okay, this is what the composting facility looked like. One of the challenges with composting waste that isn't that sort of nice, clean, like yard waste that you might see at a lot of composting facilities is that, you know, there's still that, like, that waste is, it's just not as nice. It smells worse. It attracts pests, rodents and stuff. And so what they do is they put it in these ag bags. So you can see where the ZWAD waste is because those windrows look white because it's bagged. The other thing that means is that you can't do what's called a windrow turner to aerate the pile. So you could go through with this equipment that basically just like stirs and sort of, you know, scoops up and turns the material to keep it aerated. So you have aerobic decomposition as opposed to anaerobic. You really don't want to emit a lot of methane in these, you know, at composting facilities. In the case of the bagged material, you obviously can't turn stuff that's in a big long bag. So you have to then do like forced aeration. So you would have like a like a pipe basically that's either sucking air out of the piles or it's blowing air up through the piles, and then you have to have sort of holes in the bag to allow that to go forward. It takes 14 weeks to compost material. For anybody who doesn't work in that area, you may be surprised, like, oh, that's a really long process. Okay, so these were the scenarios that we looked at. Obviously, we wanted to quantify the impacts of the sort of what they're doing. But then alternatives, most natural alternative would be just landfill the material. Just send it all to landfill. Probably what we would have done otherwise. So, let's consider that. And then of course, yard waste, we would say that goes to compost. That's pretty much always true, at least in California. Other alternatives, instead of generating power with the biogas, you could upgrade it, meaning you remove all of the trace contaminants, you also remove the CO2, and then you have biomethane. It's basically like natural gas, and you could put it in a pipeline, or you could retrofit a fleet of trucks to use RNG, just means renewable natural gas, so it's sort of equivalent to CNG. You could inject it in a pipeline and you could sell it as kind of a replacement for natural gas. Obviously, another sort of additional option that's kind of similar to what we considered with the truck fleet alternative would be you inject it in a pipeline and you kind of sell it like directly to some place that's going to use it for transportation. So you'd be sort of offsetting like diesel fuel as opposed to natural gas. The methods that we use, I won't spend a huge amount of time going deep into LCA methods. I don't know how familiar this group is with those, with the methods we tend to use. We did a hybrid process-based and physical unit input-output based method. So because I kind of straddle the boundary between like chemical engineering and civil environmental engineering, a lot of what we do on a day-to-day basis is like process design and process simulation. And so we do that to get the direct mass and energy balances at the facility. In this case, I mean, we had empirical data. So like we do sort of a bottom-up model based on what we know about how they operate, but then we can validate that and calibrate it with like the measured data, all the way to like power output and their outbound hauls for, the residual solids, et cetera. And then the physical input output piece of this is very similar to if anybody's played with the Carnegie Mellon economic input output tool, EIOLCA. It's like that, but you don't have to change things into dollars. You use physical units in this giant input output table, right? And we've been assembling this IO table for years. It encompasses all of the economy that we care about for the kinds of systems that we model. So it doesn't, it doesn't incorporate sectors that have like nothing to do with what we model, but everything that's sort of directly or indirectly valuable is in there. And then you have impact vectors that say, per unit of output in whatever physical unit you're doing for a given kind of activity or sector, facility type, whatever, here's how much of these different pollutants get emitted. Here's how much water it consumes, water it withdraws, all that stuff. So if folks have questions about that, I'm happy to go into more detail at the end of the talk. Data inputs, as I mentioned, we had access to everything. That was the awesome part about this project. And then we had part of the project team took measurements. They took emissions measurements at the composting windrows. This is actually a picture of a strategy that didn't work. So that was not how they ended up taking their measurements. They took measurements at the biofilters. You can see over here where the wood chips are, that to make sure that it was actually eating the methane. We weren't letting a bunch of methane like get through and up into the atmosphere. And then we had these crazy delivery logs and outbound logs, which were, it took a really long time to process those. And we used the Google Maps API to calculate like the route, the likely routes, and the fuel consumption for the trucks stuff. But just like the number of ways that you can spell all of these things, it's just a ton of data cleaning. So let's jump to the results. These are the life cycle greenhouse gas emission results for all of these different scenarios that we evaluated. So the first like obvious thing that you're going to see is, oh, landfilling is the worst. And it is by a lot. This is actually a fairly conservative landfilling greenhouse gas number. There's a lot of debate in the literature about what an appropriate value is for like landfilled food waste. Some of the literature that EPA has relied on, they use data that I think probably inflates like what the methane that's, the values are probably too high. is a reality. They've taken data that folks generated in a lab where they had used different kinds of organic waste, put them in a little, they're like stirring it, they're putting in buffer solution, they're feeding it nutrients to make sure that the microbes can like fully break down the material. And then they basically took that data and said, well, this is how quickly it would break down in the landfill. Obviously, that's not true. The pH would get elevated. That's going to slow the bugs down. They would run out of nutrients like locally available to them. And so that's going to slow them down as well. So I think like what EPA uses is like a way, way, way upper bound. We use a value that's about half of what EPA WARM uses for landfill emissions, but just to say it is uncertain. Composting comes out as being, there's some methane emissions from the composting. It's not huge, but it's not zero. And that does probably come, it's the cheapest option to achieve like one of the better greenhouse gas impacts. If you can clean up the biogas and sell it as a fuel to a fleet that would have otherwise continued using diesel, that offers some pretty substantial benefits. And so that was maybe one of the more expensive options, but it's definitely, it offers the best or almost the best sort of net greenhouse gas impact. Slightly less attractive to do like sell it and sort of offset fossil natural gas. And then the downside with the electricity really is just that the California grid is really clean. So this will look different for a state that has more like coal-fired generation still in their mix. But yeah, for California, electricity offsets don't look as good. Okay, so I'm going to jump straight to the social damages, because the big like oh my goodness moment that came for us was when we took the air pollutant emissions and fed them through two different integrated assessment models, AP3 and easier, that basically I won't get into the details of how those work, but they take air pollutant emissions that are precursors to fine particulate matter, PM2.5, and they estimate the formation of PM2.5, and then they take sort of local information on like population density and demographics and stuff, and these dose response curves, and they predict kind of monetized health damages associated with those original emissions that you fed into the model. And the ammonia emissions that come from composting turned out to be by far the driver of the social costs. Now, there's a few caveats to this. The first is that the degree to which ammonia will drive the formation of additional PM in the atmosphere is really location dependent. The sort of local atmospheric chemistry can be ammonia limited or not, depending on how many other sources of ammonia emissions you have around there. Like if you're close to like a CAFO, for example, you probably have a lot of other ammonia emissions occurring, or just an agricultural region in general. And so adding extra ammonia to the atmosphere may have like little or no sort of marginal impact on PM, because there's plenty of ammonia to react anyway. Whereas if you're in an urban area, you may not have a lot of other background ammonia sources. And so adding some extra ammonia to the atmosphere will drive the formation of additional particulate matter. So yeah, it made me think like, oh man, like sort of urban farming and composting is maybe not a good idea. But there's a lot of uncertainty here, and these models are still being refined. It's a known weakness that the ammonia estimates are, well, they vary a lot model to model, clearly, as you can see. So yeah, that's a challenge. And when we looked at like, okay, well, what can we do to reduce ammonia emissions from composting? The unfortunate thing is that elevated ammonia emissions are the result of doing a really good job at aerating the pile, which is important for keeping greenhouse gas emissions down. And so there are some solutions for reducing ammonia emissions. I've listed them here. But it's a challenge, and you're never going to drive those down by like, a factor of 10 or 20, right? It's probably still going to be a significant contributor to social costs. Okay, so we're going to start transitioning to the next project now. So this is a reminder of all of the plastic contamination, and the facilities that handle organic waste, like for them, this is a big economic driver, because they then have to pay for extra equipment to screen out this stuff. They'll invest in things like depackaging machines. There's all kinds of ways that you can separate out the kind of inorganic contamination like plastics. And then they have to ship them to a landfill and pay the landfill a tipping fee to take them. So they would really prefer to get cleaner material. Like it costs everybody extra money. They had to be guaranteed a much higher tipping fee themselves to accept this sort of high contamination material. It was the source of constant conflict over the years that we worked with them. We have, oh, sorry, I saw the chat. It looks like that was from earlier. Okay, so reminder, still very contaminated. So let's talk about plastic waste. Now, I think the primary motivations for reducing plastic waste generation and accumulation would be mostly around resource depletion, right? Like keeping oil in the ground. Our plastic is largely made from, petrochemical feedstocks. Avoiding accumulation of waste in landfills. Obviously, plastic doesn't really break down in the landfills. It's just hanging out here. Oh yeah. Feel free to type your questions in the chat. If I don't see your chat, somebody just like interrupt me. Should I pause? Would now be a good time to pause for questions before we move on to the next project?
Yeah, I mean, feel free, whichever you prefer. But I haven't seen any question coming out yet. I just want to remind everyone.
Yeah, no problem.
They could ask in real time by chat, or they could hold it at the end. And I guess most people really hold until the end. So
okay, all right. Well, feel free to interrupt me, like especially during slide transitions. I'm happy to stop and answer questions. So yeah, accumulation of waste in landfills, that's obviously sort of an issue for plastics. And for me, accumulation of waste in the environment is a big one. Plastics do accumulate in the environment. We have a lot of concerns around, PFAS getting into the food chain. We worry about microplastics. And so there's a lot of like not yet well quantified and understood health and ecotoxicity impacts associated with the release of plastic waste into the environment. And when we started digging into the data on how much of our recyclables get exported to other countries where we're not super great about tracking what happens to those, I do worry that we'll sort of, you say kind of check, done, recycled, we exported it to, some country that was willing to take it. And then we don't know for sure how much of that material is actually, even being properly disposed of, let alone recycled. So there are lots of potential solutions for dealing with plastic waste. And I'll tell you, I've gotten a real like crash course in a lot of these technologies. So, this is an open invitation to sort of ask me anything about plastics because, I've learned a ton in the last few years, and I do have some opinions on sort of what works and what doesn't. But you can make more compostable or biodegradable plastics. That's been mostly a failure so far. It's a small fraction of the market, and they also don't break down under realistic conditions, certainly in anaerobic digesters and definitely not in composting operations. That stuff tends to just get screened out. It's trash. It looks like any other plastic. It's not like the facilities are saying, oh, well, this bottle says PLA on it, so I'll leave it in the pile. No, they're trying to get it out as quickly as possible. There's non-plastic substitutes, which sometimes work, but the reality is like plastic's really useful. I, for one, do not enjoy drinking out of paper straws. Like I'd rather just not have a straw, which is another alternative. It's just not use it for applications where it's not really necessary, reduce demand. There are new methods for depolymerizing plastics. I say decomposing here, that's probably not a good word choice. You can depolymerize and recycle them. Some plastics are easier to do this for than others. Unfortunately, there's been a ton of research attention on doing this for PET because it's more tractable. But PET is one of the most reliably recycled, like via conventional methods, plastic that we have. And so I was like kind of lost. Like I scratch my head when I think about like how much of these research dollars we pump into recycling PET, because it's like there are other plastics that are way harder to recycle. PET is recycled pretty often. There are new or novel or drop-in plastic replacements. So we could just say, they're going to get landfilled. Why don't we just find a like low carbon way to make them out of biomaterials, and then this will just kind of be like a carbon sequestration strategy. It's not going to make a huge dent in climate change, but you just say, whatever, we don't need to recycle it. It's just like having it be bio-based carbon, and then at least we won't be relying on petrochemical feedstocks. You can introduce novel plastics that are easier to recycle and separate out from all of the other things that are in plastics that make them so difficult to recycle. So that's what I'm going to talk about today. And then, of course, infrastructure changes. There's a lot that needs to happen on the infrastructure side to enable us to more easily recover materials that we can recycle. One quick note, I've been in discussions with, Amazon, a number of other companies, and one of the lessons that Amazon learned is that, your good intentions have to translate into good outcomes. So they introduced these recyclable plastic envelopes, and MRFs, very quickly told them, look, it's a flat package. It doesn't matter what it's made out of. Like MRFs, material recovery facilities, like sorting facilities, they separate things largely based on form factor. I mean, they have optical sorters where they can differentiate between different materials. But if your thing looks like paper, if it acts like paper, which a flat envelope does, it's going to end up in a paper stream. So not only is it not going to make it to the plastic stream that can go to a recycling facility, it's going to end up as a problematic contaminant in your higher value fiber bale, your paper, recyclable paper bale. So this is one of these things where like, it says it's recyclable and they really want you to put it in a recycling bin, and down the line, if anything, it's just a problem. So what are our options? We've kind of gone through these. There are various thermochemical options that I didn't discuss, but basically pyrolysis has gained a lot of traction. I mean, you're kind of just taking plastics and going back to like one step beyond crude oil. You get naphtha out, which you then still have to send to a naphtha cracker to get ethylene. So you have failed at avoiding the most energy intensive step of the process, but it does give you like the basic like chemical building blocks that would allow you to make like virgin quality material from your plastics. Your yield isn't going to be great, but it is better than nothing. And this is the direction folks are going in Europe, where they've instituted this tax on virgin resins. I mean, dissolution, there are all kinds of chemical recycling strategies. And what I'm going to talk about today is a plastic that is, a potential replacement for something like nylon or polyurethane. And the idea there is to make it easier and less energy intensive to depolymerize, because that is key to separating it out from things like dyes and flame retardants, et cetera. And it also enables these kind of ChemSort technologies, where you can imagine having sort of staged reactors where you selectively depolymerize each component, even if it's a sort of composite material or a multi-layer material, and you can separate sort of each type of monomer and get it out, and sort of simplify some of the separations that you might have to do downstream. So this class material is called polydiketoenamine plastic PDKs. This is a collaboration with the Helms group and now the Kiesling lab at LBL and Berkeley. And so what we wanted to do is take the chemistry that Brett Helms' group had developed and look into, what does a commercial facility look like that would make this material? How expensive is it? How greenhouse gas intensive is it to make the virgin material? What does the recycling process look like? So again, we're doing process design based on like early stage results from the lab. And then how much would you have to get back at the end of life in order to make this like a beneficial process, assuming that it's more energy and sort of energy intensive and costly to make the virgin material than it is to recycle it, which, spoiler alert, that did end up being the case. So this is kind of the basic like chemistry and process overview. You have to make these triketone monomers. The kind of baseline chemistry that we started with does rely on petrochemical feedstocks, not entirely. You can get some basic acid from bio-based sources. So you end up making this triketone monomer here. Again, the temperatures are mild. One of the things that came out of this analysis was that it generates a fair amount of chemical waste, and that was something that still needs to be addressed. So just because you have a process for recycling material doesn't mean you don't generate waste. You can, and if that waste is hazardous, then you end up having to incinerate it. So at the end, you get this PDK resin. Okay, you can put it into the use phase, recycle it. It's really easy and cheap to depolymerize. I use sulfuric acid, which is like dirt cheap as an input. Pretty mild conditions. It's easy to separate out the dyes. Those tend to be like larger molecules, and they sort of crash out. Same deal with the flame retardants, any of these other things that would usually be quite problematic. And then you can recycle the triketone monomer back and make these PDK polymers again. So, what did the sort of methods look like? Well, again, we're doing process design and simulation. In my group, we use SuperPro Designer. We've used Aspen Plus in the past in cases where we really need it. But basically, having these commercial software packages are really useful. They have a lot of chemical properties and stuff built in. We do sort of cash flow analysis using like CapEx and OpEx that's based on our process models. Again, we use this hybrid process based in physical unit input-output based life cycle assessment method. We were just doing greenhouse gas inventory for this. We didn't do any other environmental metrics, at least to start. And then we had to do this material flow modeling. So a really interesting question that came up over the course of this research is like, if you were going to design a new material where you have to make a bunch of virgin material to start with, but then at least in theory, once it's in the system, assuming you're recovering a lot of it, you can recycle it like an unlimited number of times, right? You're going to have some losses every time. So you'll always have to make like some virgin material to sort of make up. But like your demand for virgin material should go down a lot at some point. And then your demand for recycled material is going to go up as those products start reaching their end of life. And the kind of dynamics of how that happens depends on what products you go into, because they have different lifetimes, right? You put it in an automotive application, that's going to be tied up in the use phase for like 20, 25 years. If you put it into furniture, that could be, I don't know, 5 years, a decade, depending on what the furniture is. But if you put it into some kind of consumer product, it might just be a few years. Food packaging, same deal. And so there are a lot of trade-offs between like sort of the type of product that is likely to allow you to recover a lot of the material, which tend to be these long-lived applications, and the type of products you're going to be able to get some of that material back and quickly start cheaply recycling it, which is pretty key to sort of getting to a better economic place. So yeah, we did our best to address this, but it's definitely an interesting question, and there's probably more to be done there. So what do our results look like? The cost is a really striking difference. These are pretty expensive to make as virgin materials, and then very, very cheap to recycle. So that's what the circular PDK resin means, like recycled from PDK waste. And so this really highlights that challenge of like, if you build an industry where you are just making nothing but virgin resin for the first like decade of your existence, that's going to be tough. You have to find a way to improve. It was also driven by the need for just a few chemicals, right? We zeroed in on DCC, one of the chemical inputs to the process, pretty early on, and said like, wow, if you could eliminate that, it would make a big difference. And the greenhouse gas footprint is same deal, driven by the same things, very low carbon to recycle, but quite carbon intensive, an order of magnitude more than conventional plastics to make these virgin PDK resins. So that was like, we had some pretty clear, mandates from these original results that there were ways to improve, and fortunately they could be pretty targeted because we knew what was driving the cost and the emissions. And then the long-term outlook and sort of the degree to which telling how these stack up with other resins, well, the recycling process is really low carbon, right? So that ends up being less carbon intensive than PET, HDPE, and definitely polyurethane. In terms of cost, we're still more expensive than PET and HDPE, but considerably less expensive than polyurethane. And then in terms of recovery, yeah, it gets back to like how much of the material can you get back? You need almost 100% to be competitive. Okay, so the revised chemistry, Brett's group in a matter of like a month was able to come up with a process that had extra steps, right? So they would typically not view that as being optimal, but they were able to eliminate DCC from the process. And so we wrote this up. This is an article that's in Press in Sustainable Chemistry and Engineering. And you can see like not that much effort, and you already are able to cut the cost of the greenhouse gas footprint by almost half. So that was really gratifying to see, and it gives us some hope that there are additional sort of iterations to be had where we can bring the cost of the greenhouse gas footprint down quite a bit. And it highlights the value of doing this analysis fairly early in the process. You might say, well, they haven't even built a pilot facility yet. Like, why do this now? But you can develop an alternative chemistry that makes a huge difference. And then you don't have to go through the trial and error at a larger scale. You can sort of virtually scale. I scale it up in silico, right? See where your bottlenecks are, make it better. And so looking ahead, in this and many other cases, we're trying to sort of match like the technological solutions with the combination of the resins that we rely on and the applications. What are the ways that we actually get these things back? There's a really interesting optimization problem to be had here. And I won't spend too much time talking about it because I know we're getting pretty close to time. But I would say, there's no one size fits all solution. Like the PDK that I talked about, obviously that's not going to be the next like super, super cheap replacement for polypropylene or like plastic films. But there are cases where, if it's more of a like leasing or rental model and the original manufacturer can easily get it back. Things like electronics, maybe automotive applications, there are cases where these may be the optimal solution, especially if you need to get things like flame retardants out to avoid the environmental impacts of leaving those in recycled material. But there's a role for all of these different sort of interesting new recycling technologies. It's just a matter of kind of prioritizing and trying to match those things with the problem they're best suited to handle. And so with that, I will stop and ask and answer questions. And my mouse actually died while I was talking, so I think I have the ability to. I don't actually think I need my mouse, so let's just go.
Great. Well, thank you so much. Thank you. This is very interesting and very relevant. I guess the floor is now open for questions. So I do Semida. I see Semida sending a question. Maybe I could just read out loud, and then there's another question from Scown.
I don't have the ability to open up the chat, so
sure, don't worry. Let me read it out for them. So the first one comes from Professor Semida, Sylvia. So what she was asking is that in the first project, why was not a scenario of waste separation as source considered? It takes time to establish, but at the end, it could avoid contamination of the organic material, and the digest could be a good product.
That's such a good question. Yeah, and San Jose in particular has a really strange source separation strategy. They do what's called a wet bin, dry bin separation strategy. And basically what that means is, and this is just for commercial facilities, right? It's like restaurants and stuff. You put like food soiled paper and food waste in one bin, and then you put recyclables in another bin. And people are they're just bad at, at separating that. Like the plastic bags and stuff should not have been in there. But I agree. And I think that the reason why we didn't explore that was not that it isn't important. I think that would be, I honestly, like, having looked into the equipment that is required to basically make up for really poor source separation strategies, I am convinced that source separation is the better way to go. Like, it's really, really energy intensive and costly to do things like separate out plastic films and all this other stuff. Like, you can buy your way out of the problem, but it costs way too much, and it would be probably simpler to just do more sort of intense source separation. So I think that's awesome. And it was just outside the scope in terms of like what that would mean. It would be a lot of like logistics modeling and figuring out, how many different extra truck routes would you add. So yeah, the short answer is a great point, and I think that would be an amazing sort of follow-on study. If anybody wants to work on the implications of source separation, email me.
Great, thank you. And now I see a few questions from Xiang Zhao. And Xiang, why don't you unmute yourself and ask, because you are already turning on your video. Please go ahead.
Yeah. Yes. Okay. Okay. Thanks, Doc. Thanks, Doctor, for your nice presentation. And I have several maybe not so professional question, but more technical based question, I think. So the first question comes to, have you tried to quantify or evaluated the effect of pH or other soil parameters on landfill gas or leachate emissions? Because for these parameters, it can have a huge impact on the maybe some metabolism of the microorganism in soils that will have a big effect on the landfill gas and the degradation kinetics that will come to different results of the landfill gas emissions and leachate, I think.
Yeah, I mean, another great point that it was something my personal group doesn't have expertise in that. Like, we're modelers. The group that I worked with, I mean, it's conceivable that we could have taken some of those measures. They did measure pH in the composting windrows. We didn't have access to a landfill. So in that project, we were limited in what we could measure by like what sites gave us sort of easy access, and also just like it was really resource intensive. The California Energy Commission that funded that project was very hesitant to support any travel. So that meant like these poor like, you know, researchers, like postdocs and stuff, were having to make really long drives every day because CEC wouldn't pay for them to have a hotel so they could get up early and start their measurement campaign. Just these like logistical frustrating things about dealing with funders. But yeah, I mean, all great points. And one of the things that bugs me so much about landfill emissions is like we don't have the top down and the bottom up need to meet. We have these top down measurements and we don't have an ability to sort of connect those with like a sort of cause and effect in terms of operations and the material that's getting taken in. And I want that so badly. And I know it would be resource intensive, but like, you know, these sort of satellite measurements and stuff, and aerial measurements where people just publish the data and the data, this thing's a super emitter. And you're like, well, why? Yeah. So if you have like a willing landfill wants to let people in and take measurements, that'd be awesome.
Yeah. Okay. Thanks for your answer. Yeah, I agree with you, because I think there are lots of parameters that can maybe have a relationship between each other and cause multiple effects on the microorganism and their metabolism. So I think it's very difficult to maybe measure, I think. And so, okay. Sorry, I think the second question is also technical based. So I think currently, you know, there's a plastic waste surge in the current society, especially in US. So I think the current landfill may comes to the high share, the larger and larger share of the plastic waste in landfills, I think. So here's a question. So have you considered the effect of plastic wastes in organic waste degradation in landfills, such as the effect of plastic waste to anaerobic degradation of organic waste, I think, because the plastic surge may give an effect on the landfill process, I think, but I'm not sure.
Yeah, you know, it's a good question. There's the sort of like spatial issue. Like if you have a lot of plastic, I mean, one of my colleagues who's a soil scientist talks about the fact that like, you know, these like very small scale spatial issues play such a big role. Like if you're on the other side of like a rock or something, like you might as well be 1,000 miles away. Like those microbes, like you know, nutrients that are on the other side of an impermeable barrier, like doesn't matter, you can't use them. And so maybe that does impact the degradation of stuff in a landfill. I would guess that, you know, on a sort of per unit of like organic material, if you're normalizing by like volatile solids content or something, it's probably the presence of plastic waste is probably not having a huge impact on like the degradation that occurs before the cell is capped off. Maybe they're like degrading and sort of leaching out things that would impact the microbial communities in the longer term. But at that point, like you are, at least at a well-managed landfill, capturing that gas. And I don't know that it's a desirable outcome to have the breakdown go faster anyway. I guess it's an interesting question. And I think, I don't know.
No, not a big deal.
That's
also a multivariate problem, I think.
yeah. Well, and microbial communities are just super interesting on their own. And I kind of wonder if some of the like EcoFab and EcoPod stuff that, I mean, LBL is spinning that up, but other institutions are as well. If there is a possibility of like doing tests where you put like microplastics or just like whole, like plastic packaging and stuff in there to see if it impacts the performance of the microbial communities. That'd be a really interesting question.
Okay, yeah, I'm also interested in this topic, so that's why maybe I asked this kind of question for your opinion or something. And for the third one might be in a large scale or perspective, I think. So, the landfill gas capture utilization might be, I think it's kind of maybe a revenue that can be gained from the waste landfill, I think. So how do you think about the sustainability perspectives of the landfill gas capture and utilization in pilot or industry scales?
Yeah, it has some technical challenges, right? The biogas that you capture from a landfill has siloxanes and stuff that are really hard on equipment. They build up and they can foul catalyst, impact your catalyst lifetime and stuff. So there are definitely like, upgrading landfill gas and using it as RNG. I don't know how many to what degree the sort of practical challenges of using that particular kind of gas impact the cost and the attractiveness of doing that. You could also like do steam reforming and make syngas and do stuff with the syngas. Like Lanzatech is pitching. I mean, they are doing that. I don't know if they're doing landfill gas, but it's conceivable. And so, and sorry, my mouse doesn't work anymore, so I can't see the chat. People have to read out these comments, but yeah, I mean, it is a revenue. I don't think it's like a big revenue source right now for landfills, but I'd love to see it become a more valuable resource. I think it's probably undervalued and underutilized.
Great.
Okay, thanks for answering that presentation. Really thanks.
Thanks.
It's a good conversation. I see Professor L. George raised the hand. So L, please go ahead.
Yes, one of the things that struck me, I mean, first of all, I really like what you're doing, and I think these kind of analyses are extremely important as life cycle analyses. One of the things I realized listening to your talk was that the characterization of what we're working with is very tenuous and very, we don't really know what we're working with very much. And I was going to say that in addition to the kind of very sophisticated analysis you're doing, sometimes there's a need for what I call exploratory experiments, where the things that you were just talking about, for example, if you would, these would be low level, low technology, undergraduates easily do these kind of things, is put together different samples of things, instrument them in fairly small scale, and measure some of these things that right now it seems like we don't have any feeling for. What's the effect of plastic, different kinds of plastic film, what the additives are in the film and how they might affect the local chemistry and the biology of what's going on in the landfill. The more I listen, I'm not in that field at all, but it reminded me of things that I did in fluid mechanics in early days before people really had a clue about things. And simple experiments sometimes point you in the direction of how you can then make a lot better progress when you start doing more sophisticated things.
Yes. One of the things that I'm pitching this like next phase of the Joint Bioenergy Institute is actually linking the TEA and LCA models with high throughput experimental pipelines and trying to do some sort of hypothesis generation, not to say that we want to be the ones to be like telling all the people in the lab, like you have to do this, but just that, it can serve as an extra source of creativity and raise questions that they might not have thought were interesting, but there's that it will yield really, really useful scientific, knowledge. And to that point, like my colleague Megan Mauter, for example, she's a modeling person, was at Carnegie Mellon, now at Stanford, and ended up sort of branching out into experimental work, because I think you do this for long enough and you're partnering with the people who are taking measurements, and then at some point, if you have the funding to do it, you're like, I guess I'm gonna have to learn to to do this and do some targeted experiments that like are sort of synergistic with the modeling. I have not gone there yet, and I don't have any immediate plans to go there. But I definitely see the value in pairing it with the sort of empirical research and using the modeling to inform the experiments you do.
Yeah, I think encouraging people who are interested in this, and they may not be as high level people, but just like, for example, you could in a landfill put a whole bunch of tubes in just randomly almost, or distributed in some way, and pull out the gases that come out and see what you learn. Yeah. You may learn nothing. Yeah. You may learn nothing, or you may learn a lot, and maybe you could put a little bit of liquid in and pull it back and measure some measurement relating to pH or the local chemistry or biology of the samples you pull out. And as I say, maybe you learn nothing, or maybe you learn a lot. But unless you try some of these things, you can't really wait to do the complete perfect instrumentation of a whole landfill. And the expense would be incredible, whereas simple things might just point you in the right direction.
Exactly. And that's what they ended up doing with the composting, was just taking spot bag samples, and it worked great. It was better than the complicated setup I showed you a picture of.
Thank you.
Good Great. Yeah, that's very nice. Samita, are you ready to? Oh, please.
Yes. Yes, thank you, Corinne, for a very interesting presentation. I'm the one who asked about the separation. And if I can comment on that first, with the separation, you would have a clean organic input, and that will give you a nice digestate that can be used in agriculture. And we have done projects on that, and in Bolivia, we found that actually, if you could price the digestate, it could actually make a big difference in the total project cost. But actually, I had another question. It is about the plastics, because many of a lot of recycling of plastics can be very energy intensive. And I'm not a chemist, so, but the example you showed indicated very, very big gains in emissions reductions, which I believe can also have at least part of it related to energy demand. And but I couldn't see that in your presentation. And connected to that, usually the plastics, when you separate plastics, they will come very mixed. You have so many different compositions, and that's one of the big challenges when you're going to recycle plastics. We're working a lot of that in Europe, because there is a new directive and a lot's going to happen. But we looked at the alternatives, and then you would have to go up very much in energy intensive methods and ways for recycling the plastics when they come all mixed. So I would like you to comment on that. On the energy tracking that you did in the project, and how you see this once you kind of, because there are some plastics, maybe you can get them totally separated, but that's more the exception than the rule, I think.
Oh, I mean, you're dead on. So the PDKs that I talked about are sort of, they are a novel polymer that is very specifically designed to be depolymerized at mild temperatures. Obviously, this has implications for how useful they are. Like, you're not going to make a coating on your car out of this stuff because you have an acid rain event and it'll just start to depolymerize, right? Like, what? There's just, at some point, like, you have these really, really stable, like, polyolefins that just don't break down. Think about like the polypropylene that gets used in like car seats. You're not going to replace that with something that breaks down really easily, because then it would break down when you don't want it to. Like, we want our plastics to be stable. And that means that when you recycle them, they're gonna be energy intensive. Like, most of the chemical recycling processes I've seen, it's modest gains in greenhouse gas emissions, like relative to just making virgin plastics. That's just how it is. And mechanical recycling is always gonna look better from a greenhouse gas standpoint, I think, of conventional, especially, well, polyolefins and polyesters. And so, that can't, if that's our goal, then we should not do chemical recycling, because there are way better ways to spend that money to mitigate greenhouse gas emissions. Like you can do it, but the goal would need to be something else. It would need to be like reduction in reliance on additional fossil fuels, or mitigation of, avoiding waste in landfills in the environment and stuff. But that's kind of how I feel. And it's a source of, when we talk to DOE, like they want greenhouse gas emissions are like they really, really think about just that, and they want everything to fit in that box. And like these processes don't really offer the kind of meaningful reductions that I think you should see relative to how much more you're going to pay to do them. So it's kind of, like what's your goal?
Yeah, but usually the goal is a combination. Yeah, you don't want to actually go towards an alternative that will jeopardize the mitigation goal. So I think that the more you go into the plastic discussion, the more complex they get, because you end up with this idea, with this problem of how you're going to solve it. If you try to solve it only at the end of the pipe, we need to look at the design, which was one of the points, if I understood correctly, that you put it in your presentation.
Yeah, I mean, one of the things they didn't put in the presentation is like, I think what we've learned over the course of some of the projects I didn't talk about today is that like, we should probably like build out the mechanical recycling infrastructure for plastics a lot, because the reality is basically what happens at a mechanical recycler is the pre-processing step for chemical recycling. And so it's all going to have to go to those facilities anyway. And then you can send clean flake to, whatever chemical recycler you need, because that's what you're going to need to make food contact material or something. The reality is like, you cannot, even if you could recover all of that plastic really clean and get it through a mechanical recycler, there are some applications where that's not going to be appropriate for safety reasons. And so I think of chemical recycling as more of like an upgrading step that you do to a fraction of material that should ideally all be going to mechanical recyclers first. So if I were in charge of, coming up with a roadmap for the US anyway, that's what I would be doing.
Thank you.
I guess it's probably a good time to conclude. Personally, I do have a few questions that I will discuss with you, Corinne, but I think in the interest of time, maybe you just conclude here and I could follow up with you later on, if you don't mind. It was a very nice and interesting discussion. I do see a lot of overlaps and in the sessions that, with what we are working on as well, in the area of plastic waste, in the area of biomass, organic waste management, etc., and also the broader context of circular economy. So please join me to thank Dr. Scown again for the wonderful presentation and for her time, with us today. It was a very nice seminar presentation, and it's just fantastic. All right, thank you so much, Corinne.
Thank you so much for all the great questions. I had a really good time. Feel free to email me. I'm sure you guys probably can get my email address. And yeah, thanks again.
Sure.